Victor is not calling us from snowy Chicago, where he just like a month ago started a professorship in statistics and data science. So yeah, Victor is an assistant professor of statistics and data science at University of Chicago and jointly a researcher at Google. Before that, he was a postdoc at Columbia, joint between statistics and computer science. And before that, he was a grad student working with Dan Roy. And Victor does super interesting, thought-provoking work at the intersection of machine learning and causal inference. And I guess that's what this title is evoking for us. So yeah, thank you so much for visiting us from Puerto Rico, making us all jealous.
Right. Okay, cool. So let me start this talk off with like a sheepish disclaimer, which is generally bad policy, but which I'll do anyways. Actually, so first, thank you for the invitation. I'm like very excited to do this. This should be a lot of fun, which feeds into my sheepish disclaimer, which is this talk was written for like a more general audience. And so there's a long like this is what causal inference is spiel at the beginning, which I'll go through a little bit quickly, but it's still in there because what we want to establish some notation. But that means like hopefully we should be a bit under time. And so also I encourage a certain level of let's say like viciousness with the questions, right? Let's like really like sink our teeth into it. So stop me if anything seems even slightly unclear.
Stop.
Okay,
no,
cool.
That's nice to have that opening there.
Okay, cool. And is this as full screen as it gets? Okay, whatever. It's easy to read. Okay, so I'm gonna right. So the title of the talk is Causal Estimation with Gnarly Covariates, which is a title born of giving a talk about two like essentially unrelated papers. So that is what the gnarly does here. So this is joint work. The first one is with Anisha Zaveri, who was a postdoc at Weill Cornell at the time, and then the second paper is with Claudia Shi, who's now a PhD student at Columbia, and Dave Bly, who I presume you've all heard of. Okay, good. Yeah, so this talk is about causal inference from observational data, which makes it a little bit more interesting, using machine learning, which makes it easier to publish, and with gnarly covariates, which just means like we're going to be in a situation where, somehow just doing like the standard, like out of the box thing blindly will be a little bit unsatisfactory. Okay, good. So causality, probably familiar to everybody. The question that we're going to be interested in here primarily, so this is just about, this is a talk about treatment effect estimation, right? And the question we want to know is if we have some treatment, so whether or not a patient gets a drug and some outcome that we're interested in, whether or not they die, and some set of covariates, what is the expected effect of intervening by assigning some new patient to take the drug, right? Like what is the actual like uplift of making this intervention, right? And of course, the trick here is that in general, there could be these possible common causes, which I'm calling X, these confounding variables, which affect both whether or not somebody takes the treatment and what their outcome is, right? Like a favorite example of mine is horseback riding. Seems to be like strongly associated with positive health outcomes in the US. So like horseback riding as a child leads to good health outcomes as an adult. And so you might naively think, hey, we should assign everybody to go horseback riding. But in practice, this is probably like due just to like the fact that only the rich go horseback riding and the rich have much better health outcomes. So another cute example, this is a graph of deaths by drowning versus ice cream production in Florida. The upshot is, hey, the trend line goes up. It looks like there's an effect, but like if you think about it for a couple seconds, of course, there's a confounder here, which is just people go swimming more and eat more ice cream in warmer months. Okay, so why not conduct RCTs? Sorry, I'm really in love with the opening spiel, and so I know it's redundant, but I'm going to stick to it. Why not conduct RCTs? The main reason is it's hard to get IRB approval for like feeding children a lot of ice cream and then tossing them in the pool, right? Like the ethics case is tricky, right? And so you can't always just simply conduct a randomized control trial. Okay, so what do you do? We want to estimate the average treatment effect, so we're going to stick with that throughout the talk. Although that's not everything I'm saying, like, also will apply to other estimates. So we're just sticking with the ATE for like sort of notational convenience for simplicity. Okay, we want this interventional effect, which remind you is not just the same as the difference of conditionals. How do we estimate this thing? Well, there's this familiar result, which is that if I have a set of covariates X, which contain all of the confounding variables and no like bad controls, then if I just do some adjustment, there is this estimand psi, which is identifiable from the observational data, where under this no unobserved confounding assumption, psi is equal to the average treatment effect, right? And so like this is going to be the workhorse result for everything that follows, right? So just simple like adjust for all of the confounders. Okay, good. So now notation, the two main characters in this talk. One is going to be the expected outcome model, and we use the notation Q throughout, which is just the expected outcome given the treatment and the covariates. And the other is the propensity score, which I'm going to call G, which is the probability of treatment given X. And I'm also just going to restrict to binary treatments throughout the talk. Okay. Okay, and so the simplest possible estimation strategy, of course, is like we look at the form of this thing psi, and we say, well, what we should do is for each of these inner expectations, conditional expectations, let's just like fit some regression in order to estimate the function Q. That's going to give us a Q hat, right? And then we're going to approximate the outer expectation just with the empirical mean, right? Okay, so standard backdoor estimation. And of course, there are other alternative, possibly smarter choices for psi hat. Okay, good. So now we come to the gnarliness in the estimation. Okay, so I'm just kind of assuming that everybody in this is actually an expert in causal inference, and so I'm blitzing through. But like, if you'd like me to slow down, just say something, and I can give a less cutesy explanations.
There are definitely some students here, so you don't have to rush through everything.
Okay,
it's sort of up to you.
Okay, good. Well, yeah. So I mean, there should be lots of time. Okay, so let me just like take a second here to like go through the slide again. Right, because like maybe this is enough already to understand what we're doing. Okay, right. So under no unobserved confounding, right, our goal is to use a data sample to estimate this estimand psi, right? So psi is going to be equal to the average treatment effect under some particular causal assumption, right? And now the question is, okay, well, how do we actually like use data to estimate this quantity, right? And well, our idea here is going to be let's look at this internal conditional expectation thing, right? Which is in essence like the prediction of y given t and x, right? Okay, and so how do we approximate this thing? Well, we can just fit a regression model, right? So like a neural net or BART or like whatever your favorite random forest model predicting y from t and x, right? Call that fitted map model Q hat. Right, and then what we do is for each unit in the data, we make the prediction for what the outcome would be under the case that that unit was treated, right? Given their actual covariates. Sorry, can you see when I highlight things on my screen?
Yes.
Okay, sweet. Okay, yeah, and then we also make a prediction for that unit of what their outcome would have been had they not been treated, right? Again, given their actual covariate status. Right, and so this inner term, right, is an estimate of this thing here, this inner term in our estimand, right, and then we just approximate the outer expectation with an empirical mean, right? But like the upshot is we're going to run a regression predicting the outcome from the treatment, and then for each unit, like predict both what would have happened under the treatment they actually received and what would have happened under the treatment they counterfactually didn't receive, and then just average over that. Okay, and this is like the standard sort of like simplest workhorse procedure for estimating an average treatment effect.
Now, do you care about rates of convergence of or characterizations of uncertainty?
Yeah, so I mean, yeah, as I say, there's smarter choices for psi hat. And so what you'd probably do in practice is just do this sort of simple backdoor adjustment with like your favorite flexible estimator, like BART or something, and then get standard deviations either through like just bootstrapping everything, or taking like the standard like non-parametric efficient like variance bound and like computing that, right? So you also have to estimate the propensity score for that.
That relies on root n asymptotics. And so
yeah,
how do you know BART does that, or random forest or anything like that?
You you know, look up to the sky and pray, I think is the answer. Yeah, I mean, okay,
that's a computer science. That's a computer scientist answer, not a statistician's answer.
Right. So a less twee answer is you know, you can invoke like, you know, non-parametric estimation results, and, you know, use something like the AIPTW and then say, oh, well, under like a suitable set of model classes, like we know we have fast enough convergence rates to invoke these like root n asymptotics. And I think that's certainly like a statistician's answer. But the sort of like cutesy, like look up to the sky and pray answer is more or less like, look, if you just care about like point estimation accuracy, right? Like it just says measured by like squared error or whatever. At least empirically, like just fitting something flexible and doing the backdoor estimation seems to consistently like work better than other things that you might do. And so, you know, this sort of like ad hoc procedure of like, you know, do the backdoor estimation with a flexible machine learning model, right? And then compute like an approximate variance by like pretending that you'd actually done the non-parametrically efficient thing and then using like the variance estimate from that guy. You know, that appears to be sort of like empirically the best option. But yeah, like it doesn't really have like a strong justification.
I think Ilya has a question in the chat. I don't know exactly.
I can just say it. So, hi, Victor.
Okay.
Thanks for dropping by. I mean, when you say empirically, it seems like what does that mean? Do you just mean you try some simulation studies?
Yeah, I just mean like yeah, okay, so empirically is too strong, but I mean like I think that's the morality tale from like the ASIC competitions. And it's also sort of been it's been consistently true in like everything I've tried, that like that's like the best available option.
You mean
now
when you say everything you've tried, do you mean synthetic data that you've tried?
Yeah, yeah. So semi-synthetic data, but like across like a variety of domains.
Well, I mean,
really want Victor to get to the rest of his talk.
Okay, sorry, I'm gonna shut up then. Sorry about that.
Okay,
you open the door for us to be vicious, so.
Yeah, no, but let's wait till he gets past the review slides.
Okay, fine.
Okay, well, so I have to say I am enjoying this. So you know, right, but okay, let's go a little bit further because there's so much stuff to
go ahead.
Next to. Okay, good. So now we're past the review slides, so you can go back to viciousness. Okay, are we? Okay, yeah. So what is there left to say here? Well, this procedure that I've just described is a little bit of a pain if, well, X is not actually the real confounders. It's just some, like, you know, you took a bunch of convenience measurements. We're not actually sure that what we measured, like, includes all possible confounders, right? And in fact, like, you know, maybe we're like a little bit fuzzy on like what the actual underlying causal relationships between our covariates and our outcome and treatment are. And these functions Q and G are nasty, right? Like we don't like really have a hope of writing down like a parametric model that we're going to believe in, right? And so, you know, these nasty twists, I think, are actually like the typical situation, right? So all of these things like more or less seem to actually occur in practice. Okay, good. So what's this talk about? So the first thing is we're going to commit ourselves to not having any parametric assumptions on the outcome model or the propensity score. And then in the first part of the talk, we're going to say, oh, well, what can you do if there's possibly actually some unobserved confounding, right? Like you're not willing to dogmatically commit yourself to the idea that you've measured everything that's relevant. And in the second part of the talk, we're just going to say, okay, and now what if you don't know so much about the actual causal relationship between everything you've measured, right? Okay, so part one, sense and sensitivity analysis. Okay, good. So the problem that we're interested in here is that causal identification always relies on this sort of absolutist notion of no unobserved confounders, right? So this is what gives us that the ATE is equal to this observable parameter psi. But this assumption is obviously insane, right? You know, there might be like constructed situations where you would be willing to believe it. But I mean, you know, you can always construct some like weird pathology where something could have snuck into your data, right? You know, like you're thinking about like ice cream and drowning, and like, you know, how do you know that there wasn't like some children's cartoon that like really advocated for like eating ice cream and like swimming very recklessly? Right, like, you know, that's a thing. It could exist in the world. You didn't measure it, right? And so, like, since you can't rule out literally everything a priori, like, is this whole enterprise just hopeless, right? Okay, and so the intuition there is like, no, it doesn't seem like it should be hopeless. Like, surely things can't, like, you know, we shouldn't have to worry so much about this kind of pathology. So how much of a problem is this really, right? This like presence of like mild unobserved confounders. Okay, and so there's like this famous historical example of this, which is Fisher, who was maybe not the greatest guy, also was a skeptic of the connection between smoking and lung cancer, right? Where part of the argument is, well, you know, maybe there's just some like unknown gene, a thing that we haven't measured, which both like gives people like a strong desire to smoke, right? Maybe it gives them a propensity towards addictive behavior, and which causes them to develop lung cancer later in life. Right. Okay. And so then like a sharp question we could ask is, well, is it really plausible that some like unknown gene could have a powerful enough effect to explain away the observed association between smoking and lung cancer? Right. So this is the sort of question we're going to want to answer here. Okay, yeah, so our goal is judge whether some like hypothetical unobserved confounder is mild relative to a large measured effect. Okay, and so this is a sensitivity analysis problem, and the high level approach that we're going to follow for sensitivity analysis is to posit some simple parametric model for the influence of the unobserved confounder, right? And then the reason that we want to do that is now we can parameterize the strength of confounding by the parameters of that model, right? And so the point there is, you know, if we want to say like, oh, is confounding like mild or strong, right? How do we formalize that? Well, now we're going to say, oh, well, if we're willing to commit ourselves to some model for how the confounder operates, right, then like the mildness or strongness of the confounder can be formalized as like a parameter of our confounding model. Right. Okay. And then once we actually have that model in place and we have specified like a strength of confounding, right, we can use our model hopefully to compute the amount of bias that would be induced in our estimate by the presence of these hypothetical unobserved confounders. Right. And so if we can write down like a satisfactory model for the influence of the unobserved confounder, then we can sort of turn the crank and translate plausibility judgments on strength of confounding into bounds on the amount of bias that could be induced in our estimate of the average treatment effect under like a standard like non-parametric estimation procedure. Right. Okay. And so, yeah, so like the upshot, we want to generate plausibility judgments on bias based on like personal subjective judgments on strength of confounding. Okay, so our prototype for doing this is going to be this paper from Guido Imbens in 2003, where he said basically, okay, let's assume that there's an unobserved confounder, which is just a coin flip, right? Like fair coin flip, right? But we don't see it. And then what's going to happen is that the treatment is going to be assigned just according to this logistic regression model, right, where the unobserved confounder U comes in as like one of the elements of the regression, right? And similarly, the outcome is just going to be in this linear model, right, where again, the unobserved confounder is going to come in as a term in the linear model, right? And so the strength of confounding here, like how strongly the confounder influences treatment assignment and outcome, is captured by these sensitivity parameters, right? So this parameter alpha is how strongly U influences the treatment assignment. This parameter delta is how strongly U influences the outcome, right? And the way that we can conduct a sensitivity analysis here in principle is first just look deep into our hearts and fix the sensitivity parameters alpha and delta, right? So just say, oh, here's like the largest values that I think that these could really be, right? And then with like alpha and delta fixed to alpha star and delta star, we can compute the MLE from this model, right? And then our bias, our estimate for the amount of bias that was that could have been introduced by this unobserved confounder is simply the difference between like the ATE we would have estimated, with the unobserved confounder there, and the one we would have estimated with no unobserved confounding. Okay, so this is the basic prototype.
Let me interrupt for a second. I'm pretty sympathetic to your claim that alpha and delta are the product of looking into your heart, but there is some substance. Like often people will take the strongest observed confounder that they know of and estimate alpha and delta that way. So it's not quite so.
Sure. Yeah. And in fact, we are going to see that we will do that. And of course, Guido did that as well. He had some procedure for doing this. Right. So yeah, I mean, it's like look deep into your heart and also at your data. And, like your heart is more like really what you do is ask some domain expert, like really how strong could like these left out effects be? Yeah, so I'm being like a little bit, maybe self-deprecating here. But yes, completely agree with that. Good. Okay, so I'm giving a talk, and the talk isn't about Imbin's paper, and so there must be some problem with it. And the essence here is basically, I said earlier, like, hey, we're going to be in this situation where we're just not really willing to commit ourselves to a parametric form for the outcome model or for the propensity score, right? Like we just don't like have some like simple world in which we know how all of the data is related. But this thing that Imbin's does is really based very explicitly on the idea that we're going to use linear regression and logistic regression, like those would be well-specified models, had we observed the unobserved confounder, right? And what's more, even if we had not observed the unobserved confounder, this model implies a particular like simple constrained parametric form for the outcome model and the propensity score model for the observed data. Right. And so, if you write down Imbin's model, this is going to like forbid the use of flexible machine learning methods like random forest and neural networks. Right. It's an assumption which is incompatible with like the actual practice that we have in like our estimation from the observed data. Right. OK, so this is the main problem we want to fix. There's also a more subtle problem with this like purely parametric approach, which is that actually like when you marginalize out the unobserved confounder U, it turns out that the implied distribution on the observed data also depends on the parameters alpha and delta, right? And so when you add in this unobserved confounder, what you're doing really is conflating model misspecification and unobserved confounding. Right, like the bias that you get, it's not clear if it's because you are now allowing like a more flexible model, right? Like something with like a better choice of alpha and delta values, or if because there was like really like bias due to confounding. Yeah, okay, and so this is like a relatively more subtle point, but it's also just like like it's somewhat tricky to write down like a parametric model for all of the data and have it be compatible with your model for the observed data. Okay, so here's the punchline, like the thing that we're going to build up to. These are Austin plots. So Austin plots are an adaptation of Imbin's approach, where the main thing is we're going to completely decouple the sensitivity analysis and the model of the observed data, right? So the idea is like now you can model like the data that you actually see in absolutely any way that you want to, and we're still going to like tell you how to do an Imbin style sensitivity analysis after the fact. Okay, so what an Austin plot does is says, okay, we're gonna parameterize the strength of the unobserved confounder by its degree of influence on the outcome, which we're gonna measure as the partial R squared of the unobserved confounder on the outcome, and by its degree of influence on the treatment, which we're gonna measure by some parameter alpha, which I'll talk about as the talk goes on. Okay. And now what we're going to do is say, okay, well, let's pick a fixed level of bias, right? Where, let's say like the amount of bias that it would take to invalidate our study. And we're going to make a plot of all of the possible strengths of confounding which would be strong enough under our model to induce that amount of bias, right? So in the plot that we're looking at, this is a study on the effects of combination medications on diastolic blood pressure, which I think I took from a paper of Jennifer Hill's. And we have chosen a bias here, 2.0, which was equal to the nominal treatment effect. So the treatment effect we got just by like naively running the estimation. And we did that estimation just by saying, okay, we're going to model the outcome with BART and the propensity score with logistic regression, right? And now we have just plotted all possible confounding strengths that would induce a bias of 2, right? Like, if there had been a confounder this strong, then that confounder could have like induced enough bias that the treatment effect, even the point estimate of the treatment effect, might plausibly have just been 0, right?
So when
okay.
you, oh, sorry.
Oh, go ahead.
When you say under our model, you mean under the model that the models that you chose for Q and G?
No, I mean, well, yes, I guess in particular, but what I mean is under the sensitivity analysis model that's going to relate the effect of the unobserved confounder to the outcome and treatment assignment, right? Which I have not yet specified, right? So the game that we're trying to play here is build some model, which is going to be our sensitivity model, which will allow us to produce this kind of plot.
Okay, and so this plot is valid under that model and under whatever you ended up selecting for Q and G in your actual data analysis. Is that correct?
Yeah, that's right.
It's conditional on all of those things.
Yes, it's conditional on all of those things. But it only cares about Q and G in terms of like, the quality of those estimation, the quality of that estimation on the observed data, right? So it's a thing which is at least in principle measurable. Yeah. Okay. Oh, go ahead.
Well, I guess I can come back to that, but I'm not sure I understand, like, what if Q and G are highly predictive, but just wrong in terms of, oh, I guess you're getting the unmeasured confounder. Okay, so I think maybe we're saying the same thing, that Q and G have to be correct in the sense that they're controlling for the confounding that you did measure.
Yes, correct. Yeah, that's right.
Okay.
Yeah. Yeah, okay, perfect. Okay, good. And so then just to help the interpretation of this plot, what we're also going to do is take for all of the observed covariates or groups of the observed covariates, we're going to include measures like the measured influence of those covariates as like reference points on this plot, right? So we're just going to like measure the observed strength of confounding from these things. Right, and so say the upshot in this plot is here we controlled for like sex, some blood work variables, socioeconomic variables, and age, right? And what we see is that only age was really strongly confounding in this data, right? And so if there had been an unobserved confounder, which we think matters like roughly as much as age, we shouldn't like believe in the results of this study. But if we're willing to commit ourselves and say, oh no, age, like we definitely knew age was going to be like radically more important than everything else, and it's not plausible we could have left out something even close to that important, right? Then we might be willing to say, oh yeah, like this effect seems like robust to the possible, like possible unobserved confounding, right? So
I have another question about that. So age is the only thing that's a strong confounder under your sensitivity model, right? Or is this a non-parametric statement?
So it's the only thing that's a strong confounder is a non-parametric statement, but the statement that a confounder as strong as age would induce a bias of about 2 is valid only under the sensitivity model.
Okay, thanks.
Yeah, okay, perfect. Okay, good. So, right. So as I said, the game we want to play is figure out how to write down a model, which is going to let us make these plots, right? And so we need to, we need an assumption relating the observed data and the unobserved confounder, right? I mean, that's intrinsically not identifiable. That's sort of the premise of what we're doing. And we're going to formalize this assumption with a generative model, right? And our desiderata for this generative model is first that the implied distribution on the observed data has to match the actual observed distribution of the data, right? So, when we marginalize out whatever unobserved confounder there is, we just have to get back our actual data distribution. Okay, the next is that our sensitivity parameters have to be like relatively easy to interpret, right? Like I actually have to be able to show these plots to somebody and say, make a judgment about this thing, and it has to be like plausible that they can do that. And we need to actually be able to like do the bias computation, right? So we need to be able to like make the curve on the plot. Okay, and so the game that we're going to play is go back to the Imbens model, right? Write it down again. So this is the functional form that Imbens assumed, right? Where we just said, oh, hey, the unobserved confounder comes into the treatment assignment in like a logit linear way, and it comes into the outcome model in a linear way, right? And then we say, well, actually, if we just rearrange the terms in the Imbens model, what we'll see is like actually it would have been equivalent to just assume that the influence of the confounder on the expected outcome is logit linear in the full propensity score, in the updated propensity score, right? So our idea here is just going to be like rather than trying to like write down the unobserved confounder explicitly and model that explicitly, what we're going to do is just model directly the propensity score that we would have seen had we observed the unobserved confounder, right? And then use that like hypothetical full propensity score as just like a term that comes into the outcome model. Okay, so this is an assumption, right? And the relationship with the Imbens thing is just motivation for the assumption. And this is certainly the most restrictive idea in this paper. This should be the unpalatable part. But you have to make some assumption, and this one seems like a particularly simple one. Okay, so now that we've decided that what we're going to do is just model G tilde, this full propensity score directly, you know, what model should we write down? And we say, okay, well, it's a model for a probability, so let's make it a beta distribution, right? And this beta, the key thing is it's going to be centered at the observed propensity score, right? Which of course it needs to be, because when we marginalize out the unobserved confounder, we want the thing that we get back to be the propensity score we actually observed, right? Okay, and now we're also going to write the concentration parameter of the beta in this slightly funny way, right? But the meaning of our sensitivity parameter alpha is that it is just a slightly reparameterized version of the concentration parameter of the beta distribution, which gives us our model for like the full propensity score. Okay, so with that in hand, we can write down the full model. So this is the sensitivity model that underlies the Austin plots and is like the main assumption of what we're doing. Okay, and so yeah, it's this beta model for the propensity score. Binary treatment assignment just works in the ordinary way, and then this conditional expectation has this logit linear dependence on the full propensity score, right? Which remember we just took by saying, hey, if you had assumed like a linear and logit linear influence respectively, that was equivalent to assuming a logit linear influence in the propensity score for the expected outcome model. Okay, and now you can see right away that this updated model is going to satisfy our desiderata of that the observed data distribution, the implied distribution on the observed data matches the actual distribution on the observed data, right? So for the propensity score, right, given only the actual observed covariates, we can just marginalize out the unobserved confounder U, right, which is just, you know, take the conditional expectation of G tilde of X given X, right? Well, that's just the mean of this beta distribution, which by construction was at G of X, right? Okay, and exactly the same thing applies for the conditional outcome model, right? So we've satisfied our first desiderata and written down a model which like brings in an unobserved confounder in a way that just has no implications at all for the observed data distribution. Okay, so the next thing is we need to actually make these plots. So can we derive an expression for the bias? And the answer is yes, right? So the trick here is just by assumption, the average treatment effect is identified once we also account for the unobserved confounder U. So if we just take this expression and plug in our sensitivity model, we get that the ATE is equal to this thing we recognize as the ATE that we would have measured not accounting for the unobserved confounder, right? This thing here is just the naive estimate that we got using only the observed data, right? Plus this extra thing, which is a bias term, right? Okay, so now we have this expression for the bias, you know, but still in terms of these unobserved confounders. But it turns out that just using some beta distribution tricks, we can derive an explicit expression for the bias in terms of the sensitivity parameters delta and alpha, and quantities that we measure from the data, right? So it's just going to rely on the propensity score, delta, and alpha.
So Victor, can you speak a little bit to the novelty of your approach in terms of the specification of sensitivity parameters, some kind of extrapolation beyond the observed data, and a situation where you're not placing any restrictions on the observed data law? Have you seen that any other work?
So I think I referenced this paper from like Alex Franks, Alex Demore, and Avi Feller from maybe a couple years ago now, which I think did this as well in like a like 2-parameter sensitivity analysis. There's also some like older work from Rosenbaum, which I think the relationship's slightly more complicated, and so like maybe let me go on to the end of the spiel, and I'll talk about.
Yeah. Well, my point is, Victor, there's a lot of literature here on this idea, especially particularly appears in the missing data literature. So it might be something you want to sort of investigate.
No. So it is true that there is like a huge literature on sensitivity analysis, right? And so like I don't mean to.
But sensitivity analysis that meets some of your desiderata. So Jamie has talked about this, way back 20 years ago and stuff like that. So I think it'd be useful to put some of your work in context.
Yeah, exactly. So actually the Alex and Avi paper, so that did come directly out of the missing data literature. And in fact, I think that the situation is basically they wrote the paper and then realized that Jamie had actually done this like 20 years previously. And so I mean, indeed, in some sense that satisfies it. I mean, I think like the novelty here, relatively speaking, is I mean the motivation for this paper was to do a version of this like no parametric requirements on the observed data sensitivity analysis that was like interpretable by humans. So like I haven't read like Jamie's actual work, but the Alex and Avi paper, the problem with that is that it just requires like specifying some like very abstract quantities and then like reasoning in terms of detailed specifications about like exponential family models. So I mean the hope here is that this is somewhat easier to use or easier to interpret, but of course it's hard to like really objectively justify that kind of thing. So yes, absolutely. Let me say that indeed, at least the objectively measurable desiderata, there are other approaches to sensitivity analysis which also satisfy it. Okay, cool.
I don't know exactly which of Jamie's proposals it is, but he has one that's extremely interpretable, where you just like the unmeasured confounder is the true, the true potential outcomes, and it has nothing to do with exponential families. I don't know. I'm going to forget the details, but it's actually it's very user friendly in terms of understanding, the sensitivity parameters are very interpretable.
That's interesting. So I'm either not familiar with that piece of work, or I looked at that piece of work and decided there was like something else unsatisfying about it, and I genuinely don't know which world is the real world that we live in. But I mean that sounds sort of like basically satisfactory. Although I'm not completely convinced that just saying that the unobserved confounder are like the true potential outcomes is like a wholly satisfactory thing from like an interpretability perspective, right? Like I might prefer to like reason more about things like, I think I failed to measure something like age, and like how strong could the influence of that be, rather than saying, well, here's what I think the outcome would have been had I measured everything, or like had I seen the counterfactual treatment status, and then ask like, well, and how much would that have influenced my views on like my beliefs about whether this person would have gotten treatment.
Yeah, I think your plot is really cool, but I don't know. I was going to say I would guess you could do something similar with Jamie's parameterization, but I'm not sure that I don't know that that's true.
Yeah, and it is something of an open question. So there's weak heuristic evidence that Jamie didn't completely solve this problem, like didn't meet all of these desiderata, which is, people continue to publish like, at a high rate on like sensitivity analysis approaches.
But there's also weak heuristic evidence that everything anybody publishes is in his 1986 paper already.
Yeah, so that's also almost certainly true. But okay, so maybe it's like moderately stronger heuristic evidence for like the interpretability thing isn't solved. As far as I can tell, like nobody actually conducts sensitivity analyses, right? So I mean like Guido's paper, which is just like objectively wrong in some sense, still seems to be like among the best cited pieces of literature here. I mean, at least when I was looking, and I think it's just like, a human can look at the outputs and like do something with it. Yeah, sorry, actually, I'm maybe I neglected to say this, like this, the idea of like, changing around the question from like, give me sensitivity parameters and then I get like, I'll give you a bias to give me a bias and I'll give you all compatible sensitivity parameters. This was actually the main idea in Guido's paper. So that was the main innovation. And like really the game that we're playing here is trying to like preserve that innovation in a way that eliminates all parametric assumptions. Good. Yeah, but yeah, I mean, it would not be shocking to me if like Jamie actually had already solved this problem completely in the late 80s or early 90s, and then just somehow it hasn't like really penetrated through to the popular consciousness.
So Victor, it's just not Jamie's work. There's a ton of work in this space, both in the missing data literature and the causal inference literature. So I think just a little bit of humbleness would be appreciated, especially because I'm one of those contributors. So
I actually can't see who is talking. Like the Zoom is just not set up in a way that.
So this is Dan Sharfstein. So
okay, yeah.
So,
right, so, yeah, okay. So then yeah.
You probably should look at some of the literature.
Yeah, you're right. And I mean, right. It was not like it's not like this idea just popped into my head and then I said, oh yeah, definitely nobody's done this. But it's true, like I don't recognize your name immediately, which does suggest that like I missed some big chunk of like what exists already.
Yeah. Okay.
Yeah. Yeah, and I certainly, so maybe let's like push through a little bit. But I'd certainly be happy to talk about this more afterwards, because yeah, like if you've already solved the problem, I'd be quite curious to know how it works. Cool. Okay, good. Okay, so bias, right? The upshot is indeed like under this Austin sensitivity model, we get a tractable bias calculation, which involves only the sensitivity parameters and the observed data. Okay, good. So in principle, we're done, right? Like this is enough to like make those plots that I showed, right? But we're not totally satisfied with this because like ultimately our goal here is to make judgments on plausible confounding strength. And to do that, it would certainly help a lot if we could just compare it to the strengths of the observed covariates. But that's kind of a pain when things are not all on the same scale. And so to help with this, we're just going to reparameterize the outcome influence away from this parameter of delta, which is the regression coefficient, to instead be on like a fixed unitless scale. And so in particular, we're just going to reparameterize the outcome influence as the partial R squared between Y and the unobserved confounder, given the covariates X and the treatment T. Okay, so this reparameterization, the annoyance is that it apparently depends on the parameter U, right? Because we have this conditional expectation in here, which depends on U. But it turns out that again, if we just like chug through the sensitivity parameter model, we're going to end up with this nice expression for the reparameterization in terms of only observed data quantities and the sensitivity parameters. right? And the point here is now just by rearranging, we can get an expression for the bias in terms of alpha and the partial R squared and observed quantities, right? So with this in hand, we can now completely make the Austin plots. And again, this theorem, it's just like beta distribution tricks and some like conditional expectation tricks. So nothing like really fancy under the hood. Okay, good. So so now we have enough of the plot that we can like make that line. Just say no for a given amount of bias. Like here's how strong the unobserved confounders would have to be. Okay, and now we want to actually like calibrate that. So what can we do? Well, we just say, and this is somewhat of an intuitive statement. Well, for a group of observed covariates Z, we could write down the partial R squared of the influence of Z on Y, given all of the other covariates and the treatment status, right? And having written down that expression, well, we can estimate that just by fitting models, like additional models for the relationship between the outcome and the treatment and all of the other covariates, excluding Z, and plugging into this equation, right? There's a similar procedure for alpha where we just like fit new models using fewer of the covariates, and this estimation procedure is just going to give us the dots on the plots, right? So it's just like a simple model refitting and plug-in procedure. Okay, good. So some examples, which I'll just fly through quickly. This is the Lalonde jobs data, familiar to everybody who's read Nuruk's paper on causal inference. So I'm using this because it was used by Guido in his original illustration. And let me actually not spend too much time on this. I'll just say the upshot of these plots is we used, I think, random forests for the outcome model and the treatment model, and then conducted a sensitivity analysis and got the answer that made sense given the form of the plots, right? So we're just recreating what Imbins did without parametric assumptions and seeing that indeed everything works in the way that we want it to work. Okay, this is Ihdp data. So the Ihdp data was a program which Ihdp was a program which provided childcare and home visits to premature infants. And this particular data that we're looking at, again, was taken from a Jennifer Hill paper, and it was meant to measure the effects of participation level in this program on an IQ test that was administered, I think, at age 3. So again, this is like a purely observational thing. Okay, now we have a bunch of measured covariates, so including like health and socioeconomic factors, like how premature the birth was, like things about the mother. Okay, and okay, I foolishly included 2 plots here, but oh, I'm sorry. The leftmost plot is the Ihdp data. The rightmost plot is again this combination diastolic blood pressure medications example. Right, okay, and so we've just made Austin plots for both of these analyses. I think in both cases we're using BART for the outcome model and just logistic regression for the propensity score. And the upshot here is basically that if you look at this plot on the left-hand side, this is the child care IQ test plot. It really looks like nothing that we measured could induce enough confounding to cause us to stop believing in the effect. Right, and so in some like subjective sense, I think like making this plot increases our belief in like the outcome of this results, right? In the outcome of the efficacy of this Ihdp program, right? And similarly for the diastolic blood pressure, again we see like something as strong as age really could have completely undermined our conclusions. So whether or not we believe in this study is really going to depend on an expert judgment about whether or not it could be plausible that there is an unobserved confounder that has as strong an influence, or like roughly as strong an influence as age. Okay, and then one last thing. So of course, all conclusions from Austin plots are predicated on this Austin sensitivity model. And so we'd like to know like whether or not that is an unreasonably optimistic model. And so this is a table showing the results of an experiment where the upshot is that in fact the Austin model tends to be very conservative in its bias estimates. So what we did is just for each of these data sets take the strongest the strongest confounder that was actually observed, and then just measure the estimated treatment effect, like with this confounder present and with this confounder not present, right? And then that gives us sort of like a non-parametric estimate of the bias induced by leaving out this strong confounder, right? And so we can, that's this like non-parametric bias here, which we're going to think of as like a ground truth for the sake of this experiment. And then what we can do is say, okay, well, if we had had a confounder which had a strength of influence as strong as the strength of influence of the measured Z, right, of the thing that we left out, we could now plug that strength of influence into the bias formula under our sensitivity model and compute the amount of bias that we would have expected under the Austin model. And what we see is that the amount of bias under the Austin model is consistently a lot higher than the actual non-parametric bias. And the intuitive reason for that is just like the amount of bias that you get in the Austin model is just sort of like a monotonically increasing function of the amount of confounding that you have. Whereas in real data, like effects can kind of cancel out, right? So you could imagine in like the blood pressure example, maybe you have a thing where young people are much less likely to take blood pressure medication, and old people are much less likely to take blood pressure medication than the base rate. So it's highly confounding. But young people have better outcomes and old people have worse outcomes. And so even though age is like highly predictive of both of these things, it's highly predictive in a way where like the confounding effects somewhat cancel out when you average across all of the data points, right? And so like the Austin plot sensitivity model just doesn't allow for any such cancellations, which ends up giving us a certain level of conservatism. Okay, good. So I have 4 minutes left for the second half of the talk, which might be slightly ambitious. Yeah, I mean, it is a much shorter half of the shorter talk. Let me just say the problem setup for the second half and then not say anything about what we actually did, because I think that's already quite interesting. Okay, so this is a paper with Claudia and Dave called Invariant Representation Learning for Treatment Effect Estimation. Okay, so the upshot here is, here's a motivating example. We want to estimate the effect of sleeping pills on lung disease. So this is a real thing that people were concerned about. Our data set is a large collection of electronic health records collected from multiple hospitals around the world. Now, each of these hospitals serves like somewhat different populations. So the distribution of records is different depending on like the particular like data set that we're looking at. But the target of influence, so this is the effect of sleeping pills on lung disease, we think it's just going to be the same for all humans, right? So that should be like the actual causal effect should be the same in every one of these data sets. Okay, and so to handle all possible unobserved confounding, like what we might want to do is just take absolutely everything we measure and toss it into a regression, right? But if we do this like sort of naively, we run the risk of including bad controls, right? That is variables that might induce bias when they are adjusted for, right? So this is just say like colliders between the outcome and the treatment, right? And so the problem we want to think about here is, well, how do we exclude bad controls from the adjustment set? Okay, so let me just repeat that. So we don't always know which variables in the adjustment set are safe to adjust for, right? And moreover, okay, this is a too subtle point. The second bullet point is too subtle for the remaining 2 minutes, but like whatever, there's some additional motivation. Okay, and now 2 examples also motivating this problem. And let me just like put like a caveat here, which is, of course, you might think like, hey, why don't we just restrict to pre-treatment variables? And like, like that's enough to handle all confounding. And like the penalty in terms of like extra variance on the outcome model is like generally small. And yeah, I think that's totally true. And the motivating problem here is not really the motivation for working on this problem. It's that I think that there is something interesting in trying to like understand the connection between the role of causality as like the thing which gives you invariance like across domain shifts and the role of causality in the estimation of causal effects. Right, so really the reason that we're thinking about this problem is that it's going to give us like a very simple concrete template for thinking about that connection. Okay, good. So like here's the causal graph, which we might have, right? So we have this like latent health status variable. We measure a very large number of proxies for it, enough proxies that we could, in principle, exactly reconstruct the latent health status. But when we're measuring all of these proxies, we might also include things which are in fact downstream of the treatment and the outcome, although it's not actually shown on this graph. Okay, now let me just say the upshot in my remaining minute. So what do we do? Like, how do we handle this problem of like, let's select only the good controls to adjust for and exclude all of the bad controls? The basic idea is to adopt invariant risk minimization. Invariant risk minimization is this predictive algorithm which uses data from multiple environments to learn what they call an invariant representation. An invariant representation just means something such that the outcome and the representation have the same relationship in each environment, right? So more precisely, that's like expectation of y given phi of t and x are the same in all environments. And the insight of the paper, which is fairly simple, is simply that this representation, this phi of t of x, will exactly exclude all bad controls and also be sufficient for causal adjustment. And the reason is just that conditioning on phi of t of x is equivalent to conditioning on the parents of y. Okay, good. And so let me stop here since I'm out of time. If there are remaining questions, we can talk about that.
Thanks so much, Victor. That was great. And if you have to go soon, or if anyone has to go, feel free to just sign off. But if anyone has questions until Victor leaves us, feel free to ask now.
Is your unmeasured confounder binary?
No, there is no explicit distributional requirement on the unmeasured confounder. It's just, it's left completely implicit, right? Like our assumption on the unobserved confounder is just in this beta distribution, right? It's that the propensity score that you would have seen had you had the unobserved confounder, the distribution of that thing can be described by a beta centered at the propensity score that you actually measured. Right, and so that's actually like a joint requirement on, I guess, like the distribution of the unobserved confounder and the functional form relating like the observed propensity score and the unobserved propensity score, right? Like there's something implicit there, but like really the game that we're playing in this paper, like the sort of like main idea is just to like sidestep the whole issue by like specifying the distribution on the full propensity score directly.
Yeah. Isn't it the case that without loss of generality, you can assume the unmeasured confounder is binary if you're already assuming there's only a single unmeasured confounder? I think that's something Paul Rosenbaum showed.
Is he assuming there's only one unmeasured confounder? Can't this be multivariate? Just so long as or does it have to be univariate?
No, yeah. So there's no restrictions at all about like the number of confounders or their distribution or anything like that.
Does the reduction to binary only apply for a single one? I don't actually know.
Yeah, so I would guess that you probably could assume my guess is that you could probably assume a binary unobserved confounder like with a sufficiently convoluted relationship between like the observed treatment assignment and like the full treatment assignment.
It seems like your original Imbens formulation had a binary confounder. Is that right?
Yeah, that's right. Yeah. So Imbens assumed a binary confounder. Yeah. So I mean, like the trick that we played here to like ditch the Imbens parametric assumptions was exactly this trick of like move from modeling the unobserved confounder explicitly to modeling it only implicitly through the full propensity score.
Right. That's nice. So can you walk me through the Austin? So I didn't completely get the Austin plot, and so I apologize for that because I was focused on something else.
Right.
I don't know if anyone else finds value in that. If it's just me, then I can do that offline or read the paper.
Yeah, no, totally. Yeah, let me. Oh well. Yeah, I mean, I think that's an important point. So yeah.
Yeah. So I mean, I think this is the novelty here. So yeah, could you just walk me through this?
Yeah, okay, sure. So so the setup here is you imagine that you have gone through and conducted like a standard data analysis,
Yep.
right? Where you have adjusted for everything you've observed, and now you have like say a point estimate and some confidence intervals based on the observed data.
Okay.
Right. And now you look at that and you say, okay, like if there was some amount of bias due to unobserved confounding, then my study would stop being interesting, right? Where that observed amount of bias might be equal to like the point estimate that you had, or maybe it's equal to like the lower bound of your confidence interval, or maybe it's some like domain specific thing where like you just say, look, if there was this much bias, like no one should like start taking this drug or whatever.
All right, so that's a fixed number that you put in.
Yeah, so it's user specified.
Okay, fine. So I put in bias of 2 here.
You put in bias of 2.
Okay, now what happens?
Okay, now what we want to tell you is every possible pair of confounding strengths. So if I gave you a confounder which influenced the outcome such and such an amount and influenced the treatment such and such an amount, it would induce a bias of 2, right? Okay, so we're going to have
this could be some big multivariate confounder, U.
Yeah. Yeah,
Okay.
so like we're not going to specify anything about you. I mean, you could be anything in the world. I'm just telling you, like, look, if the aggregate effect of all unobserved confounding in the world, right, was at least this amount of effect on treatment assignment and this amount of effect on the outcome, right, then we would have a bias of at least 2, right? And so the curve on the Austin plot, is that set of all possible confounding strengths. Right.
And so I give you alpha, and I give you a partial R squared, and I can figure out whether or not the associated bias that induces, and I find the set of all partial R squareds and alphas that generate a bias of 2.
Right? So you give me the bias. You give me the bias, and I give you the set of all partial R
squareds. I understand.
That generate that bias, right? And now the hope is like, okay. Rather than you thinking of a list of all unobserved confounders that might exist and like assigning an alpha and an R squared to each of them, right? I'm going to give you the largest alpha and R squared that we can tolerate. And then you tell me whether or not you think that like it's actually plausible that some unobserved confounder could be so strong.
Got it. Okay. So now tell me about the points.
Okay. So now the points, what we're going to do is go through and take each covariate that we actually observed and then compute the alpha and R squared from those points, like from that observed data, like the value of influence given all of the other covariates and the treatment assignment.
So for age, take an example.
Yeah.
Conditioned on sex, blood work, and socioeconomic status.
Yes.
Right. Now what? Okay.
Okay, so conditioned on sex, blood work, and socioeconomic status, and the treatment assignment, I calculate the partial R squared of age, right? And that gives me the Y coordinate
Got it.
For this dot, right? And then I do the same thing for alpha, right? Just conditioned on the other covariates, and that gives me the alpha coordinate, right? And now
the alpha is can you just tell me just remind me what alpha is? I understand what the partial R squared is.
Yeah, so alpha is, I mean, it's this parameter in the beta. So it's basically a reparameterization of the concentration parameter of the beta distribution. It's also equal to, let me see if I have the expression here. Okay, I don't think I do, but the way that you estimate it is that it turns out to be equal to 1 minus the ratio of like 1 minus G tilde times G tilde over 1 minus G times G.
Okay, so can you just go back to that thing, the beta thing? So the X here in your example, so getting the alpha, the X is what? Is it everything except age?
Yes, that's right.
So and then the U is age.
Yes.
Okay. So I got it. So does what you condition on affect the interpretation of things?
Yeah, that is a really great question. Yeah, and
so is the scale, I mean, is it all sort of the right scale of things, right?
Yeah, so okay, shoot, my laptop battery is about to die, so I'm just gonna grab a plug inside, and then let me answer that question, because yeah, I think that is actually like maybe the most like interesting subtle issue in the sensitivity analysis stuff, which might just be, hi, so my laptop battery is about to die, so I'm just gonna sit on this couch while I finish this talk. So can you get the door actually? Okay, thank you. Okay, good. Sorry about that. Yeah, okay, good. So the crux of this problem, which is what I think you're asking about, is like essentially that when I'm looking at these dots, I'm conditioning, like when I compute this, I'm conditioning on all of the covariates except Z, the thing that I'm leaving out, right? But when I make this curve, I'm conditioning on all of the covariates, including Z, right? And so because the conditioning sets are different, it's not like the interpretation of what the dots and the lines mean is subtly different.
Exactly.
Yeah, exactly. Yeah. So so that is a real problem, at least in principle. In some sense, it's just a question of interpretation. But the interpretation, it is a little bit nuanced in that, for example, you might want to hope that you could make a statement of the following form, right? You say, I completely believe in my sensitivity model, right? And I know I have two covariates, like age and age prime, right, which come into the model in exactly the same way, right? Like I'm just totally confident that like I have these two identical covariates. Oh, for fuck's sake. Sorry, my attempts to plug in my laptop were not successful. But yeah, we're just gonna imagine I have these two identical covariates, right, which I know come in exactly the same way. And then I measure one of them and I get a strength of confounding for the one that I measured. So I actually have age and I have a strength of confounding. I say, hey, look, age is just below this bias line, right? And so now I'm gonna take the strength of age, like plug it into my bias expression, right? And I know that age prime is identical to age. And so I say, oh, hey, look, my hope is that the bias here is like lower than 2, and so I can still make some conclusion, right? Like you're just like, the logic here is just you had two identical variables, you measured the confounding strength of the one that you actually observed, and so now you want to say, oh, and that's going to give you an exact expression for the bias of the remaining one. And the subtlety, as you're pointing out, is like that's not true, right? That logic is intuitive, but it doesn't actually work out, right? And the reason is just like if these two hypothetical variables, age and age prime, are dependent, right, then like the confounding strength of age given all of the remaining observed stuff excludes age prime, right? And so it's not the same as the confounding strength of age prime given everything including age. Okay, so maybe now we're all on the same page about like what the issue is. And so
it might be hard to see the issue if you just had one covariate, right? Let's just say it was make it just super simple.
Mm-hmm.
And I'm sorry if there are people with other questions, so I don't really want to hog the questions, but let's just say you had one covariate that you measured, which was gender,
mm-hmm.
male and female, right? And then you're concerned that you have, unmeasured confounding above and beyond that, right?
Mm-hmm.
And suppose you specify a bias of 2, okay? So your influence of, okay, so what we're going to do is we're going to condition on, what are we going to do here? So we're going to find, so what is the line here is going to be the partial R squared, right?
Mm-hmm.
It's going to be the set of partial R squareds and influences of alpha, influence of treatment, right? Conditioned on gender.
Mm-hmm.
Correct?
Yep, that's correct.
And then what I'm going to do is, to get the point, I'm going to take gender out, right? I'm going to go to your formula. I'm going to take gender out, and I'm going to, can you go back to your formula? Let me just, maybe this is just not the good logic here.
I think you're going to take gender out.
Go back to this beta thing.
Oh, to the beta thing.
Yeah.
Okay.
So here, right? So we're not going to condition on anything, right?
Yeah. So this might be easier to think about in terms of the partial R squared, just because the equation's written down explicitly.
Okay. Sure.
Yeah. So what you're going to do here, right?
So my point is the things on the line are conditioned on gender. right? On the curve, and the points are not conditioned on gender.
Yeah, that's correct.
And so the scale of things or the interpretation is different.
Yeah.
And so to me, that's problematic.
Yeah, no, I agree. I mean,
Like not
think
an apples to it's not an apples to apples comparison.
Yeah, right. So that is absolutely true, and I think that is like the biggest like nuance with this kind of approach. So in practice,
like I don't see it as a nuance. Right? You're calling it a nuance, but it's not a nuance. It's central.
Right? Well, okay, so I think it's a nuance in the following sense, right? What you would like to, what you want the interpretation of this plot to be is something like you look at the lines and the dots and you see, oh, here are the dots that are like close to the line or above the line, right? And then I just say, look, there's no confounder that's like even close to as strong as like any of the confounders that are close to the line or above the line. And so I like trust in my analysis, right? Or you say the opposite thing and you're like, oh, I think there could be some confounder. And so I can't really trust in my analysis, right? Like that's the qualitative interpretation that like we'd really like to be able to take away from this kind of thing, right? And I'd say that there are
but don't you want the points to be like in the same dimension? So you're not talking about feet and meters, you're talking about on the same scale of things, right?
Yeah, well, yeah, okay. So I mean, like I guess maybe there's like an aesthetic difference here. So the distinction between like what we can achieve, right, which is like the difference in these things are distinguished by a difference in conditioning sets, right? That doesn't strike me as like a distinction between feet and meters.
I was being hyperbolic. Just to make a point, right? We have different conditioning sets, right? And so I was making an analogy when you're conditioning on different things, right? Things aren't have the same interpretation.
Right. Yeah. Right. So the nuance here, actually let me just finish this spiel. I'm sorry. This is like this is quite a subtle point, and so this discussion may go for a while. And so really, anybody who's like not interested, like don't feel obliged to like stick around.
Maybe Trang has a question. She has a question. I want to make sure that.
How about we pause just for 1 second in case other people want to, go ahead.
Cool.
So this is related to Dan's point. Is it possible for you to like make the point for sex not by taking sex out, but by doubling the confounding by sex?
So you're saying, oh, what if we both what if we just like made a second like, sex variable and conditioned on that second sex variable? Right?
Yeah, something like that. So like make another sex variable with the same confounding. So you still condition on the original. Yeah.
So the obstacle there is basically like when you tried to create this synthetic variable, you would have to specify its relationship to your actual sex variable. And if it's not like literally identical to the actual sex variable, right, then you also have to specify its relationship to the treatment assignment and the outcome, right? Like if you just said
the complexity now, just with that.
Yeah, right. So I think I like that is a great idea, and like I think like sort of simulation-based approaches to like assessing unobserved confounding is like a really interesting idea, but I at least don't know how to do it, right? Like I don't think it's like a trivial thing to implement. Although I do think it's like a particular, it is a really interesting direction. Okay, good. So maybe we can go back to Dan's question, or are there any other questions before we like dive back into the void? Okay, cool. Yeah. So
I have 12 minutes. You've got 12 minutes, but I'm happy to have this conversation offline or just read your paper and where you discuss it. I'm happy to do
yeah, sure. So okay, so I mean 12 minutes is plenty, right? Okay, so this, look, there are two major obstacles to interpreting this plot in the way that you would naively like to interpret the plot, right? The smaller one is this thing which I'm calling a nuance, but right, which is maybe just like a relatively subtle point about the difference in the conditioning sets between the dots and the line, right, which I'll come back to in just a second. The gorilla, right, is that this Austin sensitivity model has like no justification beyond the fact that it gives you something tractable to look at, right? And so, like it's true, like, hey, you conducted this analysis, you saw a dot was like kind of close to the line, but under it, you want to draw some conclusion about what happens in reality. Like, you just shouldn't do that, right? Like every conclusion you make from this kind of analysis has to deal with the fact that, like, of course your sensitivity model is like misspecified for the actual data that you have, right? And so, like the heuristic way of dealing with that, the qualitative way of dealing with that is like you only trust the outcomes of these sensitivity analysis models in situations where the answer is obvious, right? So, like if you have something you think is like approximately as strong as age, well, you shouldn't just say, oh, it's like a little bit under age, and so like, maybe that's fine. You just say, hey, I can't make a conclusion here. Right. Whereas like, if we look at the other examples, right, like in this one, like the upshot is like, hey, there's nothing even close to having like enough confounding strength to like eliminate the effect here. Right. And so, when that increases your confidence in the judgment, like implicitly, this is predicated on like, hey, even the problem, even like the bias that is induced by like the model misspecification is not so problematic, right? And so that, like, I guess that this is like a weird defense of the conditioning sets difference, but like basically, if you're already willing to swallow like the poison pill of model misspecification, right? Like the pain that is induced by these difference in conditioning sets is like a comparatively like minor issue. Well, I mean, I'm about to argue that it's a comparatively minor issue, right? Okay, so in what sense? I'm just going to go back to this because it has a bigger plot. So in what sense could that be a comparatively minor issue, right? The problem that you can run into is where your reference covariate and your hypothetical unobserved confounder are strongly associated in a way that is going to cause you to underestimate the strength of the observed covariate, right? Okay, and so let me just like say this in a really concrete way, right? Like suppose that you're in some medical application where two things matter. And the two things are like race and socioeconomic status, right? Which are going to be like very strongly dependent with each other, right? Okay, and now what you did is you incorrectly only controlled for socioeconomic status, right, and left out the effect of race, right? In this non-parametric like observed data regression, right? Okay, now you have estimated an influence strength for the effect of socioeconomic status, right? Which is in some sense, like not correct because like you really would have liked to condition on the race variable as well, right? But you couldn't. Now this is only a problem for you, right? If leaving out race has caused you to underestimate the strength of socioeconomic status. Right. And so now this, I think, is a somewhat unusual situation, right? Because when you have two variables, which are quite dependent, right, and you do some non-parametric regression, like you've chosen your regression in a way that's just going to like explain your observed outcome and your treatment assignment as best as possible, right? The typical thing that you would expect to happen, right, is that your observed variable, the thing that's strongly dependent with your unobserved variable, is now going to act both in terms of like its actual causal relationship with the thing that you're trying to model, right? But also as a proxy for the unobserved variable which you're failing to model, right?
It seems like what you want as your example isn't two variables that are correlated, but two variables that have an interaction in the confounding surface.
Yes, yeah, right, exactly. So the situation where this is problematic, as you said, is exactly, so okay, right. So I'm just saying, like, look, you might just think like that your miscalculation in general is going to be problematic. And I'm saying like, oh, actually, like in general, it's just going to increase conservativeness, right? But yeah, as Betsy said, like the case where things can actually go wrong is like where you have some strong interaction effect, right? And the sense in which this is a nuance is like, yeah, this should all like in fact come with a caveat, and we talked about this a bit in the paper, which is if you think that you have some like strong unobserved confounder, you know, enough that like you really like it's a thing you definitely should have controlled for, right? This is not due diligence. It's like you think you left something out, then full stop, you shouldn't trust a sensitivity analysis probably, right? Okay, but second, if you have an interaction effect, if you think that there's a strong interaction effect between your unobserved confounder and one of your observed covariates, then the naive interpretation, right, where you just say, oh, I'm gonna like compare like where the dot is and where the line is not valid, right? And so I mean, and I guess yeah, I shouldn't be like flippant. That is like a serious caveat, right? But it's not like it doesn't sort of invalidate the whole project. It just says, oh yeah, like there is this particular structure that your unobserved confounder could have, which might cause you actually in principle to be overly optimistic when you do this thing.
I think that's helpful. I don't know what Dan was thinking earlier, but I was thinking it was like a non-collapsibility problem that really was a huge problem regardless. I see the point that it's really just a problem if you have an interaction. Why is it the case that you wouldn't trust a sensitivity analysis if you have left out a confounder? I see why you wouldn't trust this one, but like that's when sensitivity analyses are used most commonly.
Yeah, right. Yeah, right. So okay, so maybe that's too strong. All I'm saying is like if you're doing anything which is ultimately predicated on some parametric model, right? Then like, and you conduct a sensitivity analysis, right? Then the amount of bias that you have, like, I mean, you get some bias out of the sensitivity analysis, and that's related to the actual bias in like your actual data by both like, you know, like the unobserved confounding that you're estimating the effect of, and the bias induced by the misestimation or like the misspecification error of the sensitivity model.
Mm-hmm.
Right. And I'm just saying, and so like really what I'm saying is like, oh, well, if you have a thing where like, you know, your conclusions are only going to hold subject to like, you know, your assumed parametric form being at least like, you know, roughly right, you should be like highly skeptical.
Yeah.
Yeah, and I mean, of course, there are like genuinely completely non-parametric sensitivity analyses, right?
Yeah, for this reason.
Yeah, right, exactly. And so, yeah, and so, I mean, sure, if you're like your effect size is strong enough, then like you should always just prefer that, right? Like if like whatever this like Cornwall analysis will like tell you anything non-trivial, then you always should, right? Yeah, and so, right, so okay, I guess it's not a generic property of sensitivity analyses, it's a property of sensitivity analyses which come with assumptions, right? But I think this actually is a situation where like assumptions are like, it's a poison pill, but it's a poison pill you want to swallow. Because, for example, none of the examples in this paper, except for maybe the extreme Lalonde ones, but none of the other examples that we did in this paper, like you couldn't conclude anything under even like the Rosenbaum style sensitivity analysis, right? Like much less the completely non-parametric sensitivity analysis, right? So so here I'm just saying like for these examples, right? Like when we look at this, it seems somehow like helpful to know that all of these dots are like far away from the line, right? That actually does somehow like increase my like subjective confidence in like the reliability of these results, right? But like a fully non-parametric sensitivity analysis for this particular data is not enough to like rule out that the effect is just completely explained away by unobserved confounding.
I guess then the question is, do you believe your parametric assumptions enough to believe that extra information?
Yeah, and so you know, like weak evidence for saying yes is just saying, oh, hey, we have this experiment which shows that like across these like 3 fairly arbitrary domains, like even in adversarial situations, like the parametric model tends to be quite conservative, right? Like very conservative. Yeah, and then like stronger or weaker evidence or whatever is just like the sort of like classical old school parametric statistics thing of saying like, well, your model is wrong, but if your conclusions are so like radically, massively obvious under like a wrong model, right, which you think it's not too wrong, right? Like this is not like a super restrictive model. It's basically just like a linearity assumption, right? Like, if you think that like it's completely obvious under this like, definitely probably a little bit wrong model, then you kind of waggle your eyebrows and say, oh, well, that also seems like evidence that it's like true in reality as well.
Yeah, is that the case? Like that is true. When you use a parametric model to fit to observed data, it's true that a small error in the parametric model will result in small errors in your estimate in general, or like we know how to quantify that. Is that true for this?
So it's true. So this isn't in the paper, but it is true that you can show that under like if you allow the effects, like if you assume a non-parametric model relating the unobserved confounder and the outcome and treatment model, or at least the outcome model, and then you take a Taylor expansion in the sensitivity parameters, right? Then you can show that the particular model that we assume here is essentially like the first order term of the Taylor.
Oh, that is great. That should be in there. Or like,
Right.
that's like, that is, I think the reason that people are skeptical of parametric models for identification of causal effects or for sensitivity analyses is precisely because we never have those results. That's
Right.
really cool if you have that.
Yeah, I mean it's written down on a notepad somewhere, but I mean like that's compelling in as much as like, oh well, if you know that like alpha and the partial R squared are like small, then indeed the extra error terms are also going to be small. So I mean I guess that yes, exactly addresses your question of like whether or not that's actually plausible. Yeah, maybe I will make a point of like trying to actually like add it to an appendix on the archive paper or something.
Yeah, I mean, I think that's really, to me, that's crucial because that is as you said, when you pointed out your parametric model on some slide, that is definitely my sticking point. But if you can show, I also think it's really novel to be able to show that kind of result for this kind of use of a parametric model. I don't know. I've never seen it before. I haven't gone looking for it, but
yeah, no, yeah. I mean that certainly it would be interesting. If there were 4 of me, the 4th copy of me would probably go and like drag out these results. But maybe I can even the first copy of me can do it. So I mean, the reason I abandoned it was it seemed like nobody cared about this, and so now if there's at least one person who thinks it's interesting, that's maybe strong evidence that it's worth thinking about.
I mean, I think you have to sell it in a particular way. I don't think like saying we took the Taylor series derivative of a non-parametric model is going to sell it, but I definitely think that like showing that your parametric model approximates the truth, even though it's not a standard use of a parametric model, is really novel and powerful.
Right. Yeah. Okay. Good. So that, I mean, good. Well, I'm encouraged anyways. Yeah. Awesome. All right. So, are there any other questions or concerns?
I have to go.
I have to say, I do really appreciate the level of questioning here. Like we got to all of the nuances in this thing. Yeah, and it was a really fun discussion. So yeah.
Thanks, Victor.